Welcome to Pale Blue Pod, the weekly astronomy podcast that helps you feel closer to space. I'm one of your hosts, Dr. Moiya McTier.
And I'm your other host, Corinne Caputo.
And I am thrilled to tell you all that we are recording today from a tent, from a platform tent at my old Girl Scout summer camp. Mm-hmm. The flaps are closed, and we can hear the beating of raindrops because there is a storm raging outside. But there are surprisingly excellent acoustics in here, probably because of the cozy vibes brought by one of the candles that we snuck into camp, because they're not allowed here.
No, that's contraband, but I know someone who can get us a lot of stuff if we need it.
You know a guy who knows a guy.
Yeah, who knows a Girl Scout.
Who knows a Girl Scout who can smuggle in some candles.
Exactly.
Just to get the best vibes. Yeah. Okay, so we are set in our cozy scene, and today we're going to be talking about a teeny tiny topic. Nothing big.
The smallest of
topics.
topics.
It's just 3 minutes, Corinne.
Yeah. 3 minutes. That's a pop song.
Yes, we are talking today about the first pop song length amount of time in the universe. We're talking about the first 3 minutes of the universe.
That is crazy that so much could have happened in so little time. It's what I'm imagining you're about to tell me.
Yes, I'm glad you have those instincts because, so much stuff happened in the first 3 minutes of the universe. And the fact that scientists have been able to chop up the first 3 minutes of the universe into these teeny, tiny, short-lived segments where interesting stuff happened, it blows my mind.
Yeah, that feels so crazy that we can get that specific. And yet there are so many things we still don't have answers to that feel more obvious.
I know, right? There's so much stuff that we almost feel like we should know the answers to, but we don't.
100%.
So the first 3 minutes of the universe, we're talking about the origins of the universe, the creation of this big collection of galaxies and stars and other stuff that we find in space. We collectively call that explanation the Big Bang Theory, which is also the name of a TV show that I don't really love. Corinne, how do you feel about the TV show?
Okay, I don't love it, but I have to say that I failed my first road test when I was 16, and I was crying harder than I've ever cried. Oh. And I went home, and somehow I illegally streamed the Big Bang Theory, and I did that until dinner time. And that's my memory of the Big Bang Theory. It was in that one specific moment it did console me, and I don't think I ever watched it again.
Well, at least it served some purpose.
Yeah, if it helped one girl in the whole universe, that's enough.
Yeah, and who cares about the way that it has totally warped people's perception of what a scientist is or does? That's neither here nor there.
Yeah, that has nothing to do with it. It helped me pass my road test, and that's enough.
That's what matters. So the Big Bang Theory explains how the universe started, and it has been added to over time. What we know about the Big Bang now is not what we knew 50 years ago and is not what we knew 100 years ago. So this is another example of an understanding of the universe that has grown over the last century.
That's so cool.
Yeah, just like the Galaxies episode, where it's only in the last 100 years that we understood that we were living in just one of many galaxies. The short version of the Big Bang Theory says that the universe started as a point mass, so a single infinitesimally small point of space where all of the matter was collected in the universe. And then that exploded with energy and has been expanding ever since.
Whoa. I'm like, what? One teeny tiny thing has created everything.
Yeah, according to scientists' current understanding, we all started in a teeny tiny little point called a primordial atom or a primeval atom.
Oh, the first atom. The Adam and Eve.
The atom and the event.
Oh, that's good.
Yeah, that's nice.
Yeah.
So I do want to have a little disclaimer here, a brief moment of preparing for what's coming up, because I know that cosmology is a pretty heady topic. Do you, Corinne, have any feelings when you start thinking about the origin of the universe?
Oh my gosh, immediately kind of confused and overwhelmed. It's hard to think of things that big, as I'm sure you know, and that's immediately where my brain's going. When you say cosmology, though, my brain does go to cosmetology, and I'm like, that I can handle. I do think I can.
Actually, I don't think I could handle cosmetology. I have had enough trouble caring for my hair and skin in my own lifetime.
Oh my God, get on TikTok. If you get on the right corner of TikTok, they're going to teach you everything. It's a boot camp.
Ooh, love that.
But I have yet to be on cosmology TikTok.
I have not found cosmology TikTok either, but I basically live on science Twitter, and there's a big part of that is cosmology focused. So that's where I find my cosmology information on the interwebs. But if you, listener, get a little overwhelmed by the numbers that we talk about in this episode, which actually are going to be very small numbers, not necessarily very large numbers, because we're talking about the very beginning of the universe. Well, I would encourage you to, instead of focusing on the numbers, focus on the concepts that we're saying. So if I tell you the temperature of the universe at a given point in time, and then give you another smaller number later, understand that that just means the universe was cooling down over time. You don't have to remember the specific numbers if it's going to make you anxious or upset.
Yeah, this is like a heads up for anyone who is traumatized by the testing system in schools. It's like you don't need to be as specific as what year did this start.
For sure. Yeah. I just want you to get like basic concepts, basic trends that the universe carries. And I also want to warn you, if you start feeling any sort of existential dread or anxiety, remember that we are all safely resting on the same part of this fabric of space-time here on our little pale blue dot. And that these events we're talking about, they are so very far away on this cloth of space-time that we're all on, we can barely even feel the ripples of those events. They are far from us, and they cannot touch us.
I like thinking of it like that. I like thinking of any anxious topic as this cannot touch me.
Yeah. So just remember that. We're just learning some cool, friendly facts about space. So I want to kind of start with maybe the history of what came to be known as the Big Bang Theory, which I think in most of its entirety was published in scientific literature in 1931. But we have to go back a little bit further than that to understand the context, to understand where it came from. So we are going back to 1915 when Albert Einstein published his theory of general relativity. This is 10 years after he published his theory of special relativity. The difference between these is that general relativity focused specifically on the force of gravity and how it affects the behavior of the universe and how gravity interacts with this fabric of space-time.
He published special relativity first?
Yes.
Oh, okay. And then he went more general.
Exactly.
Okay.
Yes. So in this theory of general relativity, he included the Einstein field equations. These are, well, it's one equation that can be broken down into like 10 different equations, all of which describe how the shape of the universe depends on the distribution of matter. And you might be thinking, doesn't the shape of anything depend on how matter within it is distributed? Normally, yes, because we are used to thinking about shapes that are composed entirely of matter, but there's also energy in the universe, which is slightly different from matter. So it's important that it's looking at the distribution of matter because matter is where gravity comes from. So there's the connection between general relativity talks about gravity, and these equations tell you how gravity influences the behavior of the universe. Does that make sense?
Yeah, I think so. I think I have a grip on that. We'll see how, if I can merge the next part with that.
Okay, cool. So I'm calling them Einstein's field equations because that's what they are. But I think that most people, when they hear the word equation, they think of the equations that we had in elementary and middle school, like 5 + 3 = 8. You know, some sequence of numbers and operators like plus or minus that give you a value at the end. That's what an equation is supposed to be to most people, right?
Yeah, certainly to me.
Yeah, well, that's not what this field equation is like.
No, of course not. Why would it be?
Of course not. And actually, I encountered this a lot when I was in academia going through my schooling to get my PhD. People would call things equations, and it took me until now to realize that they didn't mean equation in the way that I was used to. What they think of as an equation is like a sentence almost in numbers and other symbols that describe a set of conditions, that describe a scenario. And when you are trying to solve these equations, the solution is actually the set of conditions under which that statement is true. So all of these people, all of these physicists and scientists in the early 1900s, they looked at Einstein's field equations and they were trying to solve it, which means not just adding the numbers in the statement, but instead trying to figure out what has to be true for this statement, this equation, to be correct.
Ah, I see. Okay. So like the statement is Corinne is in a good mood. And the solution is like she's fed, she's slept, she's not alone.
Yes.
She's okay.
Yes. Oh my God. Yes. Thank you. That's perfect.
Okay.
And there would be symbols, variables that correspond to like whether you're fed or whether you've slept.
Okay.
Yeah.
Okay.
It's confusing.
It just means I'm doing science every day, trying to get in a good mood.
Oh my God. Honestly, yes. I know that was a joke and you were being a little facetious, but you are doing science every day, Corinne. Everyone is. So another thing that I want to say about these Einstein field equations is that Einstein himself didn't actually get them right. He was convinced, as were most other scientists at the time in 1915, that the universe was static, that it was standing still, neither expanding nor contracting. And he, when he made the equations, saw that with our current understanding of gravity, it would only work if the universe was expanding or shrinking. So he added in this extra variable to essentially force the universe to be static. He called that the cosmological constant. And now astronomers and cosmologists use the cosmological constant to describe the expansion of the universe. So in a way, Einstein was right, but he was also doubly wrong, you know?
Mm-hmm. So like the constant is not that it's constantly still, but that it's constantly not still or not static.
Correct. Yeah, we call it a constant, but that constant is just the variable that we use to describe like the direction of motion of the universe.
Okay.
Mm-hmm. So Einstein, not as smart as everyone thinks he is, he put those equations out in 1915. People started trying to solve these equations, and in 1927, a Belgian scientist and Catholic priest named, it's a kind of French-sounding name, Georges Lemaitre.
That sounds exactly right to me.
I'm going to say it in the way that it would be said in my hometown. George Lemaitre, credited...
I think he was in Cars.
Lemaitre. So this Belgian scientist and Catholic priest was credited with finding the Big Bang solution to Einstein's field equations. And essentially, remember I said that the solution is the right set of conditions. So he had the genius idea to solve Einstein's field equations with an expanding universe. This was in 1927. And then over the next 4 years, he started thinking about an expanding universe. Other people started to agree with him. And in 1931, he then concluded that if the universe has been expanding, it must have expanded from a primeval atom. And he was the one who coined that term. So that's the Big Bang Theory in full effect by 1931.
Whoa. That is later than I thought.
Right? A lot of things in science happen later.
Yeah, I know. Everything I think happened, millions of years ago.
I know.
But that's the same way I can't comprehend my parents' life before me. Like I can't comprehend that science was being discovered shortly, before my existence.
Right. Yeah, the idea of a time before the internet is as mind-bendy as,
yes,
a time before we knew that there were galaxies.
Yes, exactly.
So would you like to know the evidence that supported this theory that grew in popularity over time?
Yes, absolutely.
Right, because, I can sit here and tell you, like, this is what the Big Bang says, and why would you believe me if I don't tell you the evidence, the data that we use to support our theory?
Exactly.
Right?
Yeah, you could tell me anything and I'm buying it, so it's probably good for you to remind me to get evidence.
Oh, okay. Well, Corinne, hopefully over the course of us doing this podcast together, you'll learn to look for the data behind claims. So there are two big important pieces of evidence that confirm the Big Bang theory. The first comes from 1929. So this is after Lemaitre claimed the expanding universe, but before he claimed that it all originated in a primeval atom. In 1929, Edwin Hubble, who you might remember from our second episode about galaxies.
I do.
At the same time that he was measuring the distances to far away nebulae, he was also calculating how fast those galaxies were moving. So he was looking at the redshift and blue shift of different galaxies, just redshift. We can do an episode in the future maybe about redshift and blue shift and that phenomenon.
That sounds like the Matrix. That sounds like the premise of the Matrix.
It is a lot less cool than the Matrix. Let me tell you, Corinne. It's so much less interesting.
Okay, well, we're going to do an episode on the Matrix, everybody, and I'm going to tell the story of the Matrix.
Yes, in that story, Keanu Reeves gets to decide if he wants to be redshifted or blue shifted.
Exactly.
That's the big decision. We can do that episode later, but for now, all you need to know is that if a galaxy is redshifted, if it appears to be redder in our telescopes than we expect it to be, that is a sign that the galaxy is moving away from us. And the redder it looks, the faster it is moving away. So Edwin Hubble measured not only the distances to these galaxies, but also how fast they were moving away from us, and found that more distant galaxies were moving away from us at faster speeds.
Okay.
So based on that, he concluded that the universe is expanding. Like that was the definitive proof that proved what George Lemaitre found just a couple years earlier.
Oh, cool. Okay.
So that's proof for the expanding universe. But what about this idea that the universe was much more compact in earlier times? Well, for that, we look to the discovery from the 1960s of the cosmic microwave background, or the CMB. The CMB is essentially the heat signature left after the Big Bang, and you can see it everywhere. So no matter where we point telescopes in the sky, we would be able to observe the cosmic microwave background.
Whoa.
Yeah, this shows us the teeny tiny fluctuations in temperature from a moment pretty soon after the Big Bang. It's actually like 400,000 years after the Big Bang, but that is pretty soon, trust me, on these cosmic scales. And because we can see how the temperature was distributed, we can also learn how matter, how stuff was distributed, because where there is more stuff, there is more energy and therefore more heat. So we can compare that signal to our expectations, based on computer models and simulations, or just based on like what we know about how matter grows. We can, I'm getting a little bit lost. It's okay. I'm going to find it. Because that signal looks the way we expect it to look under the assumption of a Big Bang model, that is proof or evidence to back up the Big Bang theory.
Okay. So we have evidence that it's expanding. We have evidence that it was once compacted. And then what piece are we missing? Evidence that it exploded?
No, I mean, that's pretty much
all we need.
Most of the evidence we need. Yeah. We can start looking for more evidence to gaze more directly at earlier and earlier moments of the Big Bang. But the cosmic microwave background was a huge win for this theory, for this model.
Yeah, it sounds like it was, I'm trying to think of a sports metaphor here, and I don't know why I would have picked that, but I can't. An ace in the hole, one of those things, a home run.
That is an interesting choice.
Me establishing myself as a sports person here.
Yeah, if there's anything the listeners need to learn about Corinne, it's that you're huge about sports.
I love sports, guys. This is a 10 out of 10. In the Olympics, Gymnastics. It's a 10 out of 10.
Oh, there was even less substance to that sentence than I thought there would be. Good. That is the amount of substance you can expect us to bring related to sports to this show.
Absolutely.
Hey there, it's Corinne. I just wanted to let you know that if you like Pale Blue Pod, then you might love Star Tripper. It's a travelogue podcast about former file clerk Festin Pixis as he searches for the zowiest experiences the galaxy has to offer. In the tradition of classic sci-fi, anime, with a little bit of Saturday morning cartoons sprinkled in, dive into the action and explore the thriving cosmos with Festin and his crew. You can listen as they zoom through an intergalactic death race, battle a mega beetle live on a popular cooking show, and navigate their way through the eerie dunes of the packaged dimension. Star Tripper has a fully immersive sound design, killer music, and is an instant mood lifter. Popular Science even called Star Tripper pure joy in a zippy little sci-fi package. 2 complete seasons and 2 space holiday specials are available to listen now wherever you get your podcasts and on Star Tripper's website, startripperhq.com.
Listening to Pale Blue Pod is a great way to learn about astronomy concepts, but it's no secret that we're not here to make you better at math. If that's the type of thing you're after, I'd like to recommend Brilliant. Brilliant is a program online and in app form for lifelong learners that replaces lecture videos with hands-on interactive lessons. You can learn about the complementary angles in a triangle by actually stretching out a triangle on your screen to see the angles change in real time. And you can learn about the center of mass in physics by trying to balance a weighted beam on your digital finger. Those are just a couple of examples. Brilliant has thousands of lessons in math, scientific thinking, and even computer algorithms, and they add new ones every single month. I think that the world really needs more people who can use knowledge and logic to reason through problems, and Brilliant is the best way to practice those skills online interactively. To get started for free, visit brilliant.org/palebluepod or click on the link in the description. The first 200 of you will get 20% off Brilliant's annual premium subscription. Again, you can join Brilliant for free at brilliant.org/palebluepod or the link in the description. And come on, have a good time getting smarter.
This Small Business Saturday, I want you to consider supporting your friendly local podcast collective. Pale Blue Pod's a part of Multitude Productions, a small business that helps creators like me and Moiya make a living in the modern media landscape, which is no small feat. For $5 a month, you get Multitude's weekly friendly debate podcast, access to Multitude's pen pal exchange, monthly live events with hosts, and a lot more. Your dollar goes further when you support indie creators like us. So whether you spread the word or spread the love with your dollars, shop small and support Multitude this Small Business Saturday. Learn more at multitude.production/multicrew.
Pale Blue Pod is an independent podcast. That means that Corinne and I rely on financial support from listeners like you to keep this whole podcast engine going. And one of the very best ways that you could support us, if you have the money to spare, is by joining our Patreon over at patreon.com/palebluepod. For just about $1 an episode, you can gain access to our director's commentary, which is a list of extra reading and resources and maybe even some fact-checking that I make every time I review an episode from all-around audio genius Misha Stanton. At higher tiers, you can get your name added to our patron star chart where we have the names and stellar properties of all of the amazing people who support us. And at an even higher tier, Corinne will write you a fake horoscope every single month. In case you're on the fence, you should know that the first 50 people to sign up for our Patreon will be eligible to receive a signed copy of my book, The Milky Way, an autobiography of our galaxy. So sign up at patreon.com/palebluepod. I would really appreciate it. Corinne would really appreciate it. All the other listeners would really appreciate it because it's, again, support from people like you that make it possible for us to make this podcast in the first place. And I will reiterate, the first 50 people to become one of our patrons will be eligible to receive a signed copy of my book, The Milky Way, an autobiography of our galaxy. I would love to send a copy of it to you. So go on over to patreon.com/palebluepod. Thanks. So you might note, Corinne, that the cosmic microwave background is the biggest evidence we have for the Big Bang, but that the cosmic microwave background is a signal left over from 400,000 years after the Big Bang. this episode is about the first 3 minutes of the universe, which is way less than 400,000 years.
Yep, you could argue that it's much less.
Much, much less. So now we're getting into the part of the universe, the time zone of the universe, where we're relying on particle physicists and like theoretical physicists' work. So I will tell you that we are leaving my comfy, happy space where all the stars and galaxies are. And we are going way, way back to the beginning of the universe. But we still have a pretty good understanding of the order that things would have happened in.
Okay.
Yeah. So now we're about to get into these teeny tiny fractions of a second after the Big Bang, because our understanding starts at what's called a Planck time. That's Planck. A Planck time is the amount of time it takes a photon, so this thing moving at the speed of light, to travel a Planck distance. Because this is the way we define things in science. It's all nested.
So funny.
I know. And it makes it, when you're trying to explain this stuff, it makes me feel so ridiculous. Because when you're defining something, you're not supposed to use the word in the definition.
Right,
but if you're defining a Planck time, it'd be like, it's the amount of time it takes to travel the Planck distance. Well, that's not satisfying.
Yeah, that's not helpful. Also, in any kind of like old school 90s movie battle against a bully, here you are like saying Planck, and they're like, see, they are nerds.
You're right, it is a very nerdy sounding word.
Yeah.
So we can measure back to a Planck time after the universe started. This is the smallest unit of time that modern scientists can measure. And at that time, during what we call the Planck era, all of the 4 fundamental forces of the universe are unified. They are essentially smushed together because all of the particles, all of the forces, all of the quantum fields that dictate these different forces are coupled. There is not enough space in the universe yet for them to act separately from each other.
Okay.
Corinne, how much do you feel like you know about the 4 fundamental forces of the universe?
Oh my God. The 4 fundamental forces. Gonna say gravity's one of them?
Hell yeah, you got that.
And pushing and pulling.
I believe you got another in you. What about what we use to see?
Vision, eyes. The force of eyes.
The force of the eye force.
Yeah, the eye force, and then touch and smell. And
what about light? Have we talked about what light is and like the spectrum that light falls on?
I know from probably my dad, but like light it's like a wave, right?
A wave and
a
you got it.
Sound?
No, it's very different from a sound. So light is both a wave and a particle.
A particle.
Yes. That particle is called a photon. And a photon can have lots of different discrete energies. So you'll have some photons that are at the energy of, let's say, 100 hertz. And that's the only energy, that's the only frequency that photon exists at. And then there's another photon that's at like 200 hertz and so on. Okay? So those are the particles. All of these particles have energies that exist along the electromagnetic spectrum.
Ah, yes.
Yes, because one of the other forces is the electromagnetic force. And then we have the 2 nuclear forces. There's the strong nuclear force, which is essentially responsible for nuclear fusion happening in the cores of stars. It like sticks the different small particles together. And you have the weak nuclear force, which among other things is responsible for particles decaying into other particles. So like if you have a neutron, for example, it can decay through different processes into like a proton and a neutrino or whatever.
Wow.
Yeah, like there are forces out there in the universe that just be taking particles and turning them into other types of particles.
Oh my God.
This is why you can't trust the universe. Things are just spontaneously turning into other types of particles.
Yeah.
It's wild out here.
How am I supposed to trust that? what happened or figure out what happened if this wasn't always right.
Luckily, we do understand many of the processes that makes particles decay into others. So those are the 4 forces: gravity, electromagnetic, weak, and strong.
It's so funny how we sometimes use words like Planck and then sometimes we just say strong and weak.
Yes. Oh, wait until we do an episode about the names of different telescopes. I would love to just rip the astronomy community to shreds for naming something the Very Large Array or the Extremely Large Telescope. Like, I fucking hate that we do it this way.
That is so funny.
What is wrong with us? Oh, okay. So the Planck era. Back to the first 3 minutes. We're actually back at the first 10 to the minus 43 seconds. So imagine a fraction, and there is a 1 on top, and on the bottom, it is 1 followed by 43 zeros.
Oh my God.
So we're talking the tiniest amount of time. All of the 4 fundamental forces were operating together. And so, like, nothing could really happen in that time frame of the universe. But starting at 10 to the minus 38 seconds, so another very small amount of time has passed. Now we're into the GUT era, the GUT era, or the Grand Unified Theory era.
Ooh.
Yeah. At this time, the force of gravity uncouples from the other 3 forces. You have gravity, and then you have this super force that is the weak and strong nuclear forces and the electromagnetic force combined. That decoupling, we think, kind of triggered the inflationary epoch. This is an amount of time where the universe ballooned. It like blew up. It went from something the size of like a nucleus of an atom to something the size of our solar system. That's a difference of like 10 to the power of 60.
Whoa.
Yeah, it got really big very quickly. Well, I mean, it's still much smaller than the size of the universe today, but compared to where it started, it got quite large. But keep in mind that the universe is still at like billions of degrees Kelvin. It is extremely hot in this universe. So we're not talking about the cold emptiness of space that we see today. We are talking essentially about a burning ball of plasma with basic fundamental particles all swirling around. Actually, we're not even at the particle stage yet. So let me get there. Right now, we're at 10 to the minus 36 seconds after the universe. After that, after inflation, the strong nuclear force uncouples from the other 3. So now we have the force of gravity, the strong nuclear force, and then the electro-weak force. That's the weak and electromagnetic forces working together.
That's a lot to do.
I feel like this is just a list of different stages, but I feel like it is really interesting that these 4 forces like separated from each other at different times.
Yeah, that's what I was wondering is why did the strong force go first?
Yeah, like what determines the order that they separated? Yeah, that's a really good question. It's because all of these forces operate at different scales and they all have different strengths. Like gravity is the one that we talk about the most, but it's actually the weakest of these forces.
Ah, okay.
And the strong nuclear force is the strongest of these forces, but it only works on very small scales, like smaller than the size of an iron atom. So when the universe is expanding during that inflationary period, different scales become relevant to the universe, and so different forces like kick in depending on the scales at which they operate.
Whoa, okay.
So now we are at 10 to the minus 10 seconds. So I guess we're at 1/10 billionth of a second.
Whoa.
I think, yeah. Particles like protons and neutrons start to form at this time. But those are like, that's matter. Antimatter also starts to form. So you have protons and antiprotons forming, and neutrons and antineutrons forming. And when you have a proton and an antiproton, they cancel each other out. And so scientists aren't sure why, but for some reason, the universe produced ever so slightly more matter than it did antimatter. So the particles won out, and there were protons and neutrons and electrons floating around in their plasma soup early in the universe.
Okay.
Mm-hmm. Yeah, so we just created particles. We're at 10 to the minus 10 seconds. We just created particles. And then for roughly like 3 minutes after that, we are in a phase of nucleosynthesis where the protons and the neutrons started coming together to form atomic nuclei. At the end of this 3 minutes, most of the nuclei were formed. Most of those nuclei were hydrogen, and some of them were helium. So it was like 75% hydrogen and 25% helium. But at that time, it was still too hot for the electrons to grab onto these nuclei. Because if you remember back to your high school physics or chemistry class, all of these atoms have a nucleus made out of protons and neutrons, and then there's a cloud of electrons flying around them. Well, these atoms, they don't have their electrons yet. The electrons are floating around in this plasma soup, and that actually has the unfortunate consequence of blocking photons, these particles of light, from escaping the early universe. They kept like bumping into electrons and getting scattered that way. So the universe is opaque at this time. We cannot see what was happening. And it took 400,000 years for the universe to cool down enough that essentially the electrons calmed down and joined the nuclei of these atoms. So we formed neutral atoms for the first time, and the photons no longer bounced off of electrons, so they were able to roam free, and we have a transparent universe.
Whoa, that's so hard for me to imagine.
A universe that's opaque.
That can't be seen.
Yeah. It is a weird thing to think about, because you have to imagine the actual journey that these photons take to get to us. Would you like to guess what temperature the universe had at that moment, which we call recombination, the moment of recombination, which is silly because the electrons and nuclei weren't combined before. Why are we calling it recombination when it hasn't been combined before? I don't know.
Okay, well, it was extremely hot. I'll talk in Fahrenheit, which is 1 billion degrees.
Oh my God. No, not quite. Yeah. So it was around 3,000 Kelvin. So it was about 1,000 times hotter than it is now. That's about 5,000 degrees Fahrenheit.
Wow.
So those were the first atoms, and then the first stars didn't form until 300 million years after the Big Bang.
Oh my
And that's
gosh.
when you get into the part of astrophysics that I'm more familiar with.
Yeah, what was happening in between?
The atoms were just chilling, I guess.
Figuring out what they want to do.
They were moving around. Yeah, I mean, the universe would have been too, even after the formation of these neutral atoms that would be mostly hydrogen and helium gas, the universe was too hot, was too warm for those clouds of gas to condense into stars, because you need to actually cool down a cloud of gas before you can trigger the star formation process. You know, like cold makes things contract.
Yes.
Right?
Me.
Things that are hot, they expand. So you need a chill breeze to trigger star formation.
Okay, that makes sense. It's the season of stars. It's fall. The cool winds coming in.
Oh my God, yes. Yeah, last month you couldn't have made any stars, but listeners, this month...
This month you can.
You start those star-making factories.
This month you can try it.
Just cold enough to start contracting some gas clouds.
Just in time for the holidays, the holiday rush.
Yeah, so that's the first 3 minutes of the universe. Corinne, how you feeling? Do you have any questions? How's your anxiety?
It is, you know what I can feel my brain doing? Immediately it's like, we're going to stop thinking about that. It's like, no. It's on a scale that is so hard to comprehend. It is so much more productive than me is another side of it.
Look, Corinne, you are a human. You're not supposed to be able to do this much in 3 minutes.
I can't make a universe, no. I just don't think I do much in 3 minutes.
I know. Yeah, me neither. I could like a really successful poop for me is one that takes less than 3 minutes. Like that.
Yeah.
Anything else takes longer to be good, but a long poop I think is less satisfying.
Yeah. If you put a lot of pressure on me, I can maybe do something. I'm trying to think of anything I can do in 3 minutes. Probably.
Could you like make a smoothie or something?
I could make a mess. I could make a big mess.
Yeah. Oh, hell yeah. We can make a
Which
mess.
I guess is kind of what the universe did.
Absolutely, yeah. I actually, exactly that. It made a big mess. It created a big thermodynamically complicated system where entropy was indeed always increasing.
I can do that. I can do that on a small scale. In my kitchen?
Mm-hmm. Yeah, you mentioned scale earlier as something that like brought some anxiety or overwhelmed you. Is it the scale of space?
Yes.
Like distance, or is it the scale of time?
I think it's both. I think it's that things have existed for so long and will for so long, and I am but the smallest blip.
Mm-hmm.
And I don't really think about my importance often. Like, that doesn't really bother me, but there's something just like inherently a little like fearful in, oh my God, what am I doing here? What are we doing here?
Oh, yeah. I like to think back to, this cloth, the fabric of space-time, and each one of us is just a single stitch in this cloth.
Yes.
But we're still part of it. Like, we are still a natural part of it.
That does make me feel better.
Okay, good. Because I understand the urge to get overwhelmed and anxious when you start thinking about these big scales. I really do. But these big scales aren't going to hurt us.
That's true. That's true.
It is not a lion.
They can't get me.
We do not have to let our heart rates, go up because of it. Do you have any, questions, anything that you want to clarify?
Yes. Okay, so I do have the questions that everyone's got on their minds. What came before this Big Bang?
Oh, we're starting easy.
Are we?
No.
I'm like, oh, great. We can breeze through these.
This is like the hardest. Absolutely not. This is, I think, one of the hardest questions to possibly answer, and it veers sharply into philosophy, I think.
Okay.
And unfortunately, I don't think any of these answers are very satisfying, because it's either nothing existed before the Big Bang, but then you have to start asking what started it? What was the catalyst? But then there's another equally valid school of philosophical thought that's like, it doesn't matter what came before it. It just started. Before this, I was reading about Stephen Hawking had this starting point hypothesis that if you imagine the universe's shape through space and time as a shuttlecock, as the birdie that you play with, that has a rounded edge. So at the very end of it, it does start from zero, but we don't have a hard time understanding that it just started. And another person described this same theory as would you ask what was south of the South Pole? No, it's round. It's a spherical surface. So it the South Pole just starts. It is the starting point. So
interesting.
I don't think either of those answers is very satisfying. One potentially satisfying answer that I don't think is correct has to do with the potential ways that the universe could end. And one of them is that the universe expands, but then slows down the expansion until it stops, and then shrinks back in on itself until it gets to that single point again.
And repeats?
And then it repeats. Yeah, it rebounds. And in that scenario, what came before the Big Bang was just another universe, where we're in this constant cycle of expanding and contracting.
Whoa.
So yeah, but we don't think that that's right. So I don't think there is a satisfying answer to what came before the Big Bang. We don't have a concept of time before the Big Bang, so science can't answer this question.
Whoa. I'll figure it out and get back to you.
Okay, cool. Yeah. And then let me know when you figure it out, and we can contact the American Astronomical Society. And we'll get you your credit.
Okay, no problem. Okay, so then I think what I'm thinking about is what came before it? What was it existing in? Where did this Big Bang happen?
Yes. Okay. So remember that the Big Bang started with all of the stuff, all of the I guess at that point it was just energy of the universe in an infinitesimally small point.
Okay.
So then that infinitesimally small point expanded, which means that the Big Bang happened everywhere. Because the Big Bang happened in that point, which then expanded to the universe we see now. And that's why you can see the cosmic microwave background in any direction, because the signal from the Big Bang is all around us, because the entire universe experienced the Big Bang.
Whoa.
Mm-hmm. We actually have this thing in astronomy called the cosmological principle. And it's like the foundational set of rules that underpins almost all of cosmology. And it tells us that the universe as we observe it is both isotropic and homogeneous, which means the universe looks the same from every single point within the universe, and the universe looks the same in all directions.
Not me. I have a good side.
You are not isotropic and homogeneous.
No, not me.
No. That's good. I don't think I would want to see a truly isotropic human being.
No way.
That sounds like one of those like terrifying, biblically accurate descriptions of angels from the Old Testament or something.
That's so funny. Yeah, what would that person look like? I'm imagining, like, this is not the answer at all, but like Professor Quirrell in the first Harry Potter movie, where it's like, there's a face on both sides. Like,
there would be a face on all sides. It would just be a ball of face. It would suck.
It would suck. That's so funny. Okay, so what does this have to do with dark energy?
We're still trying to figure it out. So sometimes people say that dark energy is what's fueling the expansion of the universe, and that's actually not true. The universe was expanding and would expand even without dark energy. It expanded at the beginning of the universe when there wasn't dark energy present, or it was present, but it wasn't dominating the motion and behavior of the universe. So dark energy is not responsible for the expansion. Dark energy is responsible for the accelerating expansion of the universe. And we're still trying to figure out what dark energy is. One hypothesis out there is that kind of like gravity is a natural consequence, or it's like inherent to matter. You know, if you have matter, you will have gravity. Some people believe in this force, a fifth fundamental force called quintessence. And that says that something inherent to the lack of matter is this quintessence force. So when there's matter, gravity will pull it together. When there is no matter, this dark energy will push things apart.
Interesting.
And that's just one hypothesis. I really like it because it's a nice symmetry, but that is just one hypothesis. We are still actively trying to figure out what dark energy is.
Yeah.
But I do think that we'll have more of an answer soon. I would be willing to put money on us knowing more about dark energy on big scales in the next 20 years.
Oh my God, I love that. I love hearing that because I think when I hear about it, there's part of me that's like, I can't believe here I am just going to die not knowing what that is. As if I've dedicated my life to this, like any number of scientists have. I'm like, I'm better off knowing nothing about it.
You are super invested. Well, Corinne, after this podcast, you might be pretty invested.
That's true. That's true. I might have to switch my life around. Okay, so I'm going to figure out what came before the Big Bang, and I'm going to figure out what dark energy is, and I'm going to get back to you.
Thank you. Those very small, achievable to-do items.
Yeah, I'll loop back.
Oh, hey, Corinne, did you know that I made a Twitter account for the pod?
I saw it followed me.
Yeah.
Everyone go follow.
So yeah, I bring that up because, listener, you can go follow us on Twitter at Pale Blue Pod, which is the name of the show. So we've made it easy for you. Please go follow us there. And please go follow me on various social media platforms at Go AstroMo.
I am also on Twitter and Instagram at Corintellectual, which is just intellectual with the C-O-R in the beginning.
I love that. It's a good, is that a portmanteau?
You know, maybe.
You'll also check on that and
I'll also check on that. Okay, I have 3 takeaways from this.
Good. Oh yeah, it's a good rule of 3 here. Okay, well, if we have nothing else to say about the origin of this grand universe that we all call home, then I will sign off and tell you to stay spacey, listeners.
Yeah, stay spacey, everyone.
Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this link to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.